People that are gone, I'm going to record this. A capacitor is called a capacitor because it has the capacity to store charge and energy. So you should always be thinking, bigger capacitance means more capacity to store charge and energy. Okay, so like that, it should come with that. So you guys built a really, really basic circuit. It was just, hey, you had a battery, you had a capacitor, and the symbol for a capacitor is two lines like that because it's two parallel plates. And then let's say there is a switch right here, and we hook this up. So I want to talk about what happens when a capacitor gets charged. So the first thing I want to make sure you understand, okay, a battery does not supply charge. Or, if you go and you plug something into an outlet, your outlet is not supplying charge. Your battery, your outlet, is supplying energy to move the charges that are already in the wire. So like we're going to talk about, how a capacitor gets charged. Okay. So the first thing I want to make sure you realize is that, okay, charges are already in the wires. So I don't want you to think, that, you're getting charges out of the batteries. You're not. It's just the charges are already there. Okay. So the charges are already there. So here's what happens when you start with a neutral. If you start with a neutral capacitor, this graph is super duper important when we're talking about capacitors. So this is like when you're thinking about a capacitor, you need to always be thinking back to this. If you have an uncharged capacitor, it starts right there. There's no charge, there's no voltage across it. You can kind of think of it like if it's uncharged, you could think of it as, hey, I have two ponds, and the two ponds are at the same level. So like there's no potential difference. There's 0 volts across from this plate to this plate. There's no potential difference. Okay. Well, when I close the switch, here is what actually happens. When you close the switch, that positive charge that's already in the wires, well, it gets pushed away from the battery, which then gets pushed onto the capacitor. So I want to make sure you guys understand. It's like, hey, this gets pushed, push, 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 push. So when this is closed, push, 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 and it adds a positive charge to the battery. Do you guys understand that?
How does the positive get pushed?
Because there's lots of positive charge on the positive side of the battery. And so that once I close this positive charge pushes this one, and then pushes the next one, and pushes the next one, and so on. And it ends up getting pushed onto the capacitor. Is that okay?
Yeah, thank you.
You betcha. Well, guys, if I push a positive charge onto here, I'm going to push a positive charge off the other side. Does everybody understand that? If I'm pushing a positive charge off the other side, what charge is the other side going to get?
Negative.
It's going to get a negative. So that this, where when you close the switch, okay, so when you close the switch, positive charge builds up on the positive side and pushes positive charge off the other side. Hence, the other side is going to get a negative charge. Everybody's so far so good, everybody? Well, this process is going to continue. So just so you know, like that maybe would be like, hey, that's where I am on my graph. Do you guys with me? I have a little bit of charge. There's a little bit of a potential difference. So it's kind of like this. You know, like between my two ponds or between my two plates, there's a little bit of a potential difference. Okay, there's a small potential difference. Well, then more positive charge gets pushed on. It's going to push more positive charge off the other side. More positive charge gets pushed on, pushed it off the other side until your loop rule is completed. So when I say until your loop rule is completed, well, if the only thing in your circuit is the capacitor and the battery, then that means the voltage across here has to equal the voltage across there. You guys with me there? Okay. Okay. You know, if there's other things in your circuit, it's, you know, this continues until your loop rule is satisfied. So, you know, charging continues until loop rule is satisfied. Okay. So if this was 10 volts, you would also have 10 volts across your capacitor if the only thing in your circuit is a capacitor. Okay, obviously if there's other stuff in your circuit, then that wouldn't be the case. How am I doing? Everybody with me so far so good?
When you say like 10 volts, would that mean, for example, like the positive side would have +5 and then the negative side would have -5 volts?
Sure.
Okay.
So that eventually, just so you guys understand, you know, from here to here, this would be, you know, fully charged. You know, biggest potential difference. And that would be like this point up here. How am I doing? Is everybody with me so far so good? Questions? Other questions so far?
Wait, could you like re-explain how you were saying the positive charge gets pushed off? Like I was a bit confused. Pushed off of what?
Yeah, thank you for asking that. All right. So this is my positive side of the battery. This is my negative side. So I have lots of excess positive charges here. So these excess positive charges are going to push against the positive charge that's already in the wire and push against the positive charge that's already in the wire, positive charge already in the wire, already push, 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 push. And then it's going to deposit one positive charge here. Now this positive charge is going to push a positive charge off the other side. So if I lose a positive charge, that's going to become negative. And then that process is going to continue where it pushes another positive charge on, push a positive charge off the other side, push a positive charge on, push a positive charge off the other side, and so on. Is that okay, Navia? Or no?
Oh, sorry, I was just nodding.
Oh, okay, I didn't see. I'm sorry. Okay, all right. Good, good. All right, so far so good, everybody? Good. Does everybody understand why the graph starts here and then it goes up like this? Does everybody understand that piece okay? All right, so let's talk here because this, like I said, this graph is super duper important. The slope of this graph tells us C. Is everybody with me? Which then means, well, slope is rise over run. So C is going to be equal to Q over V. And yes, if you look on your equation sheet, okay, you will see that's one of your equations on your equation sheet. It's written a little bit different, but it is there, okay? The area of this graph well, the area of that would be 1/2 base times height. Is everybody with me there okay? Well, we already know Q times V is the energy of a capacitor. So that's how much energy is stored in your capacitor. And again, if you look at your equation sheet, it's right there. Okay, this one is just taking this other formula and plugging it in, but it's there. Okay, how am I doing? Is everybody with me so far? So good there, guys. I had a lot of you just go, oh, well, to find energy, it's just Q times V. That is true. Why can I not just go Q times V for this graph, though? Like, hey, here's my ending V, here's my ending Q. Why can't I just go this Q times this V and get my energy?
Because it's a triangle.
It is a triangle, yes, because is your capacitor always at this charge? It is not. I want to make sure you guys really follow and have it make sense that the capacitor starts here, and then as it builds up charge, it builds up voltage, which is why it's that 1/2 piece. How am I doing? Did everybody follow that okay? All right, there is a question on your lab, so let's talk about this question because, again, I want to make sure it makes sense, where it's saying, hey, you know what? If you were to this V, and then it said, if I double the V, so let's say I double the V. So I go to here. All right, so let's talk, okay? All right, so if I double the V, what happens to the capacitance?
It doesn't change.
Right, nothing happens to the capacitance. On the graph, what is staying the same that shows you that?
The slope.
The slope is staying the same. Is everybody with me there okay? In real life, the area, the separation, the dielectric is staying the same for your capacitor. Okay, that's how you change the capacitance. Okay, but if I double this, then C is staying the same. Does everybody understand why? If I double this, what happened to my Q?
It doubled.
And you can see that. I went from here to there. That doubled. Is everybody with me there okay? But my energy did not double. If you look, does everybody see the area of that piece? Do you see how many triangles you have now? Oh, I got that one, I got that one, I got that one, I got that one. Oh yeah, my energy would be times 4. Because if you look, this is times 2, and that's times 2. Which means your energy is times 4. Does everybody follow that okay? Okay. Are there any other questions relating to the lab that I didn't answer that you guys want me to go over more with you?